Hello, I'm Rudolf A Römer here at the University of Warwick. I'd like to tell you a little bit about some of the work we've recently done on the calculations of higher order local and non-local correlations for one-dimensional strongly interacting Bose gas. And the work was done together with colleagues Nandani, Tan and Guan, and it was actually our PhD student Nandani who did most of the hard calculations. So like I said, we'd like to study the one-dimensional Bose gas case, and we're doing it with a repulsive delta function potential for n interacting particles in the one dimension. And I'm sure many of you are aware of this is a very typical way in which you write the Hamiltonian. And already I realize I've forgotten closing brackets here. So important factor is we have h bar squared over 2m out. This Hamiltonian in the paper appears in equation number 1. Here we just have the kinetic term, and we have a strength of the interaction, which is our parameter c, which will be important as we go along. And then what we would like to compute is actually the m particle local correlation function. So if we have the ground state psi denoted as this, we'd like to compute the following correlation function, namely we have the normal annihilators and gradation operators, but then we do it at a local position without loss of generality. Let's assume this is at coordinate 0, and we generate m such particles there, and then we sort of destroy them. And that's the correlator. So this is now the main result of the paper. This is the m particle local correlation function, expressed in terms of m, in terms of little n, which is the particle density, number of particles divided by system length, and expressed in terms of gamma, where gamma is nothing but sort of a rescaled interaction strength, namely c divided by, again, the particle density, and expressed in terms of alpha, where alpha is actually a generalized exclusion statistics parameter. So we haven't just derived this result for bosons, but we arrived it basically for anyons. And this is the prefactor, and this is followed up by another term here, and this term captures the finite temperature dependence. So this isn't just the result for zero temperature, but the result actually holds for finite temperature. And this particular formula, which is formula 51 in the paper, holds in this temperature range from finite temperatures up to the quantum degeneracy temperature. And the quantum degeneracy temperature in 1D defined as usual as h bar squared over 2m times n squared divided by kBt. Now, we have also straightforwardly calculated the result at temperature T equals 0, and that's expressed in formula 48. And clearly then if you take the limit here, we recover the T equals 0 result. And we've also derived an approximate formula, an approximate temperature dependence for larger temperatures, and that is in equation 54 in the paper. And these are sort of the main result, this is sort of the main result that we're having, which means that we're given an explicit construction in the relevant quantum temperature regime for the m particle local correlation function. Okay, that's it. I hope you liked the abstract, and I hope you liked the paper. And like I said in the beginning, if you have any questions, feel free to send us an email. Bye-bye.